This is for gases. So as you can see now, here we've got a whole bunch more levels indicated. So here we've got the ground vibrational state, okay? And then here we've got the excited vibrational state. And you can see, for one, the first one that I'll point out, okay, the Q branch. So this is showing multiple lines to the Q branch, which is not correct. That's a bad figure. There will only be one line for the Q branch, okay? And so the Q branch is when it truly goes from nu equals 0 and j equals 0 to nu equals 1 and j equals 1, okay? So we'll start by noting that in the Q branch, we have a nu plus 1. So I'm going to write I know the way I'm writing that looks kind of goofy, but that's kind of standard spectroscopy notation. Nu goes to nu plus 1. And delta J equals 0. All right? And so we're going to call this set, this transition, I'm going to call that nu tilde sub Q. And I'm going to say that equals delta S, which is a function of quantum number nu and a function of quantum number j. And I'm going to talk more about what this delta S function is momentarily. Okay? So now, what about the P branch? Okay, well here we've got the P branch over here, and let's just find one to make an example out of. So if we look at this very first line right here, so it's in the nu equals 0 and the j equals 1, and it goes up to the nu equals 1 and the j equals 0. All right, so you can see here for the P branch, delta j is -1. And of course, we recall we can only move one j value at a time, right? So we're not going to have a delta j equals 2 or anything like that. And of course, we're still talking about the fundamental transition here, okay? And so now we're going to come up with an equation on the next slide, this delta S equation, okay? And we shall see that we'll start with the same form here, but the way this is going to go, so that's delta S, so any one individual S is going to come from nu plus 1 and j minus 1. Okay? And over here with the Q branch, we'll note that that's nu plus 1 and just j. You'll see what I'm going to do with these equations on the next slide. And now if you look at the R branch, where you can kind of guess where this is going, here if we start at nu is equal to 0 and j is equal to 0, this goes up to the nu equals 1 and j equals 1. Okay? So for our R branch, we still have, right, the fundamental transition, but now our delta j is plus 1. We're going to come up with an equation to describe those transitions in the same way. Okay, so the delta S is going to give us the actual energy of that vibration, right? Remember, the difference in energy levels is what we observe in spectroscopy. And now this S function is going to be nu plus 1 and j plus 1. Okay? So let's do some algebra with this thing. And if you want to follow with me, go for it. Okay? So the P branch, right? We recall, we said that was this delta S as a function of nu plus 1 and j minus 1. And so now when I go to write this equation down, okay, this is the delta, right? Final minus initial. So that's going to be S of nu plus 1 and j minus 1. So this is my final. And now my initial is just going to be nu and just j. All right, so that's my initial. Okay? And so how do we get all of these? Well, we remember that the vibrations follow this. Let's just do the simple equation, right? Our vibrations follow this delta G equation, okay? And our rotations, let's see if I can go all the way back to the rotations. Where'd we go here? Yes, okay. And our rotations follow this, this F equation, right? J times J plus 1 times B. Okay, so that's what we're going to do. So let's put all of that together. All right, so first I'm going to start with the initial, because that's likely easiest to see right away. And so this whole initial state is going to be given as nu plus 1/2 times nu tilde. So we know that, and if I were, of course, to put in nu is equal to 0, right, then I would have it. And now that's going to be plus j times j plus 1 times b tilde. And so when we do these other two, the Q branch and the R branch, all of our initial states are going to look like this, where I just have to supply the correct quantum number, right? And that would be j is equal to 0 and nu is equal to 0. Okay? But something magic happens when we take the time to do the algebra. So let's code in the let's write down the final state. Okay? And so now that's going to be nu plus 1 plus 1/2, right? So we're doing this generically. So I've substituted nu for nu plus 1. Okay? And that's still times the vibrational energy level nu. And then now this is going to be plus, and this is going to get a little hairy, so hopefully I've left myself enough room. So I'm going to replace this j with a j minus 1. Okay? And then I'm going to replace this j with a j minus 1, and that's a j minus 1 plus 1. And now that's all times b tilde, right, the rotational constant. And there's my final state. Okay? And so now I'm not going to do all of this algebra, but if I were to do this algebra, right, distribute all these things through and treat this generically, and I'm going to treat it generically by not putting in a value for nu. We could, if we wanted to. We could put in 0 for this nu, and it would all work out, right? If I put in 0 right here, then 0 plus 1 is 1, and we haven't done anything illegal. Okay? But if we were to keep all of this through and do the algebra on this, we would come up with the following equation. It would be equal to nu tilde, remember that's the energy level, or the actual, the actual energy that would show up on the spectrum, the vibrational constant, minus 2 times j times b tilde. And that's what we would get. It would be this simple little equation right here. Okay? So I'm going to write that down again so I can keep it all boxed off. So nu plus, or nu p, the p branch, right, is nu tilde minus 2j times b. And so what's pretty cool with this, it doesn't matter what the vibrational quantum number is because we're only ever dealing with the fundamental transition, right? But now when we start talking about the j levels, you can see what's going to happen as we go up in j levels, right? If j were equal to 0, then that whole thing goes out and the vibrational energy is just equal to the vibrational constant, right? But what if j is equal to 1? Okay, well, if j is equal to 1, that's going to go nu minus 2 times b prime. Okay, well, what if nu is equal to 2? Well, then that's going to go nu minus 4 times b prime. Well, what if nu is equal to 3? That's going to go nu minus 6 times b prime, or b tilde, sorry. And there's something really cool going on here. So I'm going to back up really quick and go to back to our microwave rotational spectroscopy. And recall here that we said these rotational lines will be spaced every 2 times b. Right? Not quite. Obviously, we also remember there's some centripetal distortion, right? But in general, they're spaced every 2 times b. And so what's really cool, what we just did, this was the kind of the little magic that I was talking about. Here we can see now each of these rotational lines will be spaced every 2 times b, which is super cool. Okay? So if we were to repeat this process for the Q branch, where now my nu sub q, right, we know is equal to this delta S function, which is just going to be nu plus 1 and j, okay, which is just going to be equal to, let's see here, nu plus 1 and j for my final state, and my initial state is just going to be nu and j. So if we were to put all of that together, then simply all that it equals is just nu. So one line for the Q branch. And in fact, if our gas, so remember, this is only for gases, right? Our Q branch is where the liquid form of this gas would show up in the IR spectrum, right? Because you can see there's no J dependencies, all right? So if we were looking at like HCl, okay, and I'm going to show you the IR spectrum of HCl next, as a liquid, there'd only be one vibration, the hydrogen-chlorine vibration, right? And it would show up at this value. But if it were a gas, however, we're going to see these rotational lines. And I'm going to cut straight to the chase here. And if we were to do the same thing for the R branch, I'm not going to write any of this down, right? You could work it out for yourself if you like. But if we do all of this for the R branch, then we get that this equals 2 times the rotational constant times J plus 1. Okay? And so once again, if we were to go through a series of J values, right, if J is equal to 0, then this is equal to 2 times B. So I did, what did I do? I did something wrong. Oh, this is, excuse me, 2 times B times J plus 1, sorry, plus nu prime, right? So if we were to go through these levels, right, for J is equal to 0, that's going to be 2B plus the vibrational wave number. So I'm going to put tildes on there so we know that those aren't quantum numbers. If I were to look at the J equals 1 state, right, that's going to be 4B plus nu. If I were to look at the J equals 2 state, 6B, etc. So we're going to see spacings every 2 times B. Okay? So